Welcome to my channel Arunkumar at examguru. This video will be dealing with the subtopics related to fluid mechanics, and there will be 5 multiple choice questions on basic fluid properties. Question 1: which of the following statements are true? Option A: the solids maintain definite shape and volume. Option B: the liquids maintain volume but not shape. Option C: the gases does not maintain shape and volume. Option D: all the above. Now let's consider the 3 states of matter: solid, liquid, and gas. And let's look at the microscopic view of each of these states. If you look at the microscopic view of the solids, the attractive cohesive forces among particles are very high, that is, they are tightly packed particles, as you can see in this view. And if you look at the view of the liquid, the space between the particles are larger compared to that of solids. So that means the attractive cohesive forces among particles are less compared to solids. In the case of gas, the space is more than that of liquids. That means the cohesive forces among particles are less compared to liquids. Now, the term fluids represents liquids and gases in fluid mechanics. In the case of solids, the solids maintain definite shape and volume. In the case of liquid, so when we transfer the liquid from one container to other, the volume remains same when we transfer liquid from one container to other, but shape changes to that of new container. Hence, the liquids maintain volume but not shape. Now, in the case of gas, the gases does not maintain definite shape and volume. Hence, when you compare solids, liquids, and gas in terms of shape and volume, the solids maintain constant shape and constant volume. Liquids does not maintain shape but maintains constant volume. Gases does not maintain shape and volume. Hence, for question 1, the correct answer is option D, all the above. Now let's move to question 2. The unit of dynamic viscosity of fluid is option A, Pascal second, option B, Newton second per meter, option C, Newton meter per second, and option D, Pascal. Now, dynamic viscosity or absolute viscosity is the property of fluid which offer resistance to movement of one layer of fluid over another adjacent layer of fluid. And kinematic viscosity is denoted by V, is the measure of a fluid's internal resistance to flow under gravity, and V equals mu by rho, where rho is the density of fluid. So these are the definitions of dynamic viscosity and kinematic viscosity. Now let's look into details of both these types of viscosity. Now before that, we should know the fact that there are 2 types of flow that is encountered. The first one is laminar flow, where the fluid molecules are in layers, and in the second case, turbulent flow, the fluid molecules have random orientation. Now this is the volume of laminar fluid at rest. The fluid molecules are assumed to stay in horizontal layers as shown for laminar flow. So there is horizontal layer 1, horizontal layer 2, horizontal layer 3, 4, and 5. There are 5 horizontal layers for this given volume of laminar fluid. Now, what happens when we move this fluid over to another cylinder having the same diameter as the depth of fluid? Now, so when the fluid enters the cylindrical pipe having the same diameter as depth of fluid, that is at t equal to 0 seconds. Now, what happens when t equal to 1 seconds? The relative movement of layers of molecules occur after 1 second. Now, what are the observations on velocity profile of the relative movement of fluids after t equal to 1 seconds? The point number 1, the layers touching the boundary of the cylinder, that is layer 1 and layer 5. So you can see in the figure, layer 1 and layer 5 touch the boundary of the cylinder. They will be at rest, that is 0 velocity, because the boundary is at rest. The middle layer, the layer 1, layer 3, will have maximum relative movement, so has maximum velocity. So you can see in layer 3, it has maximum velocity. And point number 3, hence there is a change of velocity of layers along the depth with 0 at the boundary and maximum at the center of the cylinder. Yes, the velocity profile is marked where it changes from 0 and reaches the maximum at the middle. Now what are the observations related to when it is initially at rest and when the fluid is after motion of 1 second? There is change in cross section of the fluid after motion, so there is change in shear deformation. There is rate of change of shear deformation theta along horizontal axis, that is in x direction, d theta by dx. So you can see in the figure along the x direction there is a change in shear deformation. And the third point is there is change in velocity of layers along depth, that is in y direction, that is there is du by dy. U represents the velocity over the depth, which I have already mentioned in the previous, that there is change in velocity over the depth with 0 at the edges to maximum at the center. Now it's proved theoretically that rate of shear strain, that is d theta by dx equal to du by dy, that is velocity gradient. Newton's law of viscosity states that shear stress generated in a fluid is proportional to the velocity gradient. That is, shear stress tau is proportional to du by dy, and removing the proportionality you get tau equals mu du by dy. Now shear stress tau equals mu du by dy, where mu is coefficient of viscosity or dynamic viscosity or absolute viscosity. Now the units of viscosity, you know that shear stress has the unit Newton per meter square, and the unit of velocity is meter per second, unit of y is meter. So interchanging, you will get the unit of mu as Newton second per meter square. We know that 1 Pascal equals Newton per meter square, hence we get the unit of mu as Pascal seconds. So in SI, the unit is Pascal second or Newton second per meter square. In meter kilogram second units, the unit is kilogram force second per meter square, and in CGS units, the unit is poise. 1 poise equals 10 raised to minus 1 Pascal second. Now let's compare the flow of honey versus that of water. At 20 degrees Celsius, the dynamic viscosity of water is 1.06 into 10 raised to minus 3 Pascal seconds. And at 20 degrees Celsius, the dynamic viscosity of honey is 1.36 Pascal seconds, which is 1000 times that of water. Hence, the flow of water, and when we compare with the flow of honey, honey takes more time. The time taken for honey to flow is higher than that of water. So dynamic viscosity of fluid is the measure of internal resistance to flow. Since honey takes more time to flow, it means it has more internal resistance, and that is because the dynamic viscosity of honey is higher. So the unit of dynamic viscosity of fluid is option A, Pascal seconds. Now question 3, the unit of kinematic viscosity of fluid is option A, Pascal second, option B, Newton second per meter, option C, Stoke, option D, Pascal. Kinematic viscosity is the measure of fluid's internal resistance to flow under gravity. So V equals mu by rho, where rho is the density of fluid. So two different liquids can have same dynamic viscosity but different kinematic viscosity because density of liquids are different. From the relation it's very clear. And its SI unit is meter square per second, and its CGS unit is Stoke. So 1 Stoke equals 10 raised to minus 4 meter square per second. So question 3, the unit of kinematic viscosity of fluid is, so the right answer is option C, Stoke. Question 4, the effect of temperature on viscosity of fluid is, option A, increases with increase in temperature, option B, increases with decrease in temperature, option C, no effect, option D, either increase or decrease. Now the viscosity occurs due to cohesion among particles in liquids and molecular collision in gas. Now let's take the liquid, and you look at the microscopic view. The liquid particle is acted upon by attractive cohesive forces from all other fluid particles. So the cohesive forces or cohesive bond is shown in the figure by means of dotted blue lines. Now in the case of gas, this is the microscopic view, and you can see the molecular collisions, which is responsible for viscosity in gas. So what happens when we heat the liquid sample? So this is the microscopic view of the molecules of liquid sample before heating. There will be cohesive bond between the liquid particles. So when we heat it, what happens? This is the microscopic view of liquid molecules after heating for 5 minutes. You can see the microscopic view before heating, and after heating, the heat energy is used to reduce the thickness of bond or cohesive forces among the molecules. So after heating, the thickness of the cohesive bond has reduced. So there will be less cohesive force, that means there is less viscosity of liquids, hence increase in temperature, decrease viscosity of liquids. Now what happens when we heat the gas sample? So this is a gas sample before heating. You can see there will be small molecular collisions. What happens when we heat the gas sample? So gas sample after heating, if you look at the microscopic view, you can see the heat energy is used to increase the kinetic energy of gas particles. Hence, molecular collisions increase rapidly. Greater molecular collisions result in greater viscosity of gases. Hence, increase in temperature increases viscosity of gas. Now, what happens when we apply pressure on the liquid sample? So it's a liquid sample, and we are applying the pressure by the piston. So when pressure is applied on liquid, the liquid particles come close together, and hence the cohesive forces increases. Hence, increase in pressure result in increase in viscosity of liquids, because when the particles come close together, the cohesive bond increases. Now, what happens when we apply pressure on the gas sample? So these are the gas molecules on an empty container. You know that the empty container has air molecules. So when we compress with the help of a piston, when pressure is applied on gas, the gas particles come close together, and hence there is less space available for molecular collisions. Hence, increase in pressure result in decrease in viscosity of gas, because the space available for molecular collisions are less, and hence there will be less molecular collisions. So how we are going to summarize the effect of temperature and viscosity of liquids and gases. The arrow mark upward denotes increase, arrow mark downward denotes decrease. So what happens when temperature is increased? Cohesion of liquid particle decreases, hence viscosity decreases, and molecular collision increases, and hence viscosity of gas increases. And what happens when we increase the pressure? There will be increase in cohesion of liquid particles, and hence there will be increase in viscosity of liquid. There will be decrease in molecular collision of gas particles, and hence there will be decrease in viscosity of gas. So what happens when we decrease the temperature and pressure? All the results will be just opposite. So question 4, the effect of temperature on viscosity of fluid is, the right answer is option B, increase with decrease in temperature. Now question 5, the effect of pressure on viscosity of gas is, so the right answer will be option B, increase with decrease in pressure. So thank you. Don't forget to like, share and subscribe, and press the bell icon for more updates.